me show you how to be a good breezy and change your predictions.
Hey, Hugo Bown Anderson here, data and AI scientist, consultant, and educator. I'm a friend of Alex, and I was on episode 122 of Learn Bayesian Statistics, talking about learning and teaching in the age of AI. If you're a data scientist or software engineer building with LLMs, and especially if you've hit that wall where your prototype works sometimes but isn't reliable enough to ship, I've got something for you. I'm teaching a 4-week course called Building LLM Applications for Data Scientists and Software Engineers. We focus on the actual software development lifecycle, agents, evals, logging, structured outputs, debugging, all the messy parts you have to get right to make LLM apps work in production. I teach it with my friend and colleague Stefan Krautchik, who's currently working on AI agent infrastructure at Salesforce. In the course, you'll also hear from folks like Shreya Shankar, Ines Montani, Zach Muller from Hugging Face, and Samuel Colvin, the creator of Pydantic. These are people actually building and shipping real systems, not just talking about it. On top of this, students get over $1,500 in cloud credits from Modal, Google Cloud and Gemini, Logfire, Hugging Face, and more. That means you can build and test serious stuff without worrying about infrastructure costs. The course is live and hands-on. Every week we're coding, iterating, and debugging together. We're excited to offer you all 10% off as friends of the podcast. The link's in the show notes. You can also go directly to bit.ly/LBSfriends, all one word. Would love to see you there.
Can you give us an overview of what simulation-based calibration, SBC, is and why it's so important in Bayesian modeling?
Yeah. So simulation-based calibration, we like to call it simulation-based calibration checking, just to underline that we are not actually doing any calibration, not calibrating the model, but checking if the model would be calibrated, or if the inference and the model implementation together would be calibrated. So it's kind of you could, in a way, think of it as a check for your model implementation and inference algorithm together, that they are working as you would expect. What I mean by model implementation, especially now with PPLs, so probabilistic programming languages, you essentially, you don't need to write your own samplers anymore, but you define your model in something that's a bit more accessible, and then the sampling algorithm hopefully is already there for you, made by some other brilliant minds. So in simulation-based calibration, we essentially we check that the way you've written your model is actually, like, the goal is to check that you haven't done mistakes in model implementation and also your inference is working. And how we approach this is that we draw first realizations from prior. You come up with, usually that's an easy part, you somehow randomly draw from your prior parameter values, and then you generate prior predictive data from those parameter values, which is also usually an easy step. And if we step a bit further and look a step a bit further away and look at what we have now, that we have these parameter values and some data, well, this should actually be, if you condition on the data, then the distribution of these parameter values should just be your posterior. So, and what, now we've managed to essentially create a posterior sample without any model fitting. But then, if we want to now compare if our inference is working properly, we actually run the inference algorithm to this prior predictive sample, and we again receive a posterior from our MCMC samples or from our variational inference or whatever we use for having this posterior approximation. And now we can compare this to the original parameters that we drew from the prior. and these should be from the same distribution, conditional on the data. We repeat this many times and essentially do some test for this, if it holds that they are from the same distribution. And what has been handy is just to rank the prior draw among this posterior sample that corresponds to that particular prior, and that particular draw and that particular prior predictive sample. And if our inference is working as we would expect and want it to work, then this rank should be uniformly distributed. So that's where the uniformity test then comes also in, that I was mentioning earlier.
Yeah, and
Yeah.
also, so can you hear that?
I heard, yeah.
Yeah, okay.
That's
So
huge. You have a
As-
very large bee in your office.
yeah, exactly. So thankfully that's not that. But as Murphy's law states, anything that can go wrong will go wrong. Well, this is exceptional because they are doing some remodeling of my building, and today was like super calm, nothing, no noise at all. And today, exactly as we started recording, they started piercing the wall, like here, on my balcony. So it's
Okay.
absolutely terrible, and I well apologize for that, but absolutely could not control that. So what I will
No.
do though is I will make my questions as brief as possible, especially when the noise is here. So, so thanks in advance for your patience there. Thanks. That's a great presentation and summary of what SBC is. To make that clear, maybe two things. One, that can be done on the prior specification of the model, but then also on the posterior to see that the model is actually well calibrated. And I think you recommend doing both. And then you can go into, well, that very new paper that you have out with other authors, which is exactly about posterior SBC and how to do that. And second, how can people do that, like concretely? Listeners who just listened to you and were like, oh yeah, that sounds good. That sounds great. I definitely want to try that in my models. If I'm using Stan or PyMC or any other PPL, how can I do that?
Prior SPC or posterior SPC or both?
Both.
Both. Okay, everything. Well, for prior SPC, it's quite simple. Like if you can code this prior predictive generation yourself, then you can just basically code it yourself. But also for both PyMC and for Stan, there are already packages. For Stan, there's a package called SPC by Angie Moon and Shi-Young Kim and Matti Modrak and myself, which essentially gives you very good framework for running SPC and also then assessing the uniformity. So also it gives you the framework for doing the actual computation, but also then assessing the results. And then for Python, there's a package called Simuk by Arvis developers, which also does the same, at least for PyMC models and Bambi, and I think some other models too, but now I'm not super certain about that. But that's also there ready. If you have a PyMC model, you can just give it to the package, and it will do run SPC for you and give you some calibration assessment plots already. This might take a bit while because you need to refit your model multiple times. In the R package for Stan, you can do parallel inference very easily. So essentially SPC, you would be generating these prior predictive samples multiple times to get an overall assessment for uniformity, but you can if you have a cluster or something at hand, you can just put them there, have these simulation iterations essentially run as parallel as you want. For posterior SPC, which I didn't yet even explain, but essentially our new paper, this standard way of SPC that I was now describing has a few issues or drawbacks. Essentially, if you have very vague or weak priors and some nonlinearities in your model, you might have regions of the parameter space in the prior that where the model inference is somehow not working. Like you have very pathological parts of your prior space, which you would maybe not even see in your real data. Maybe you would, maybe you wouldn't. But anyway, so prior SPC might give you essentially a false positive, saying that, well, in a way false positive if you then would go and fit your model to data that would not produce a posterior in this problematic area. So we have been developing posterior SPC, which in its simplest form, you just replace the prior from prior SPC with posterior, and you create posterior predictive samples. So you essentially focus in the area of the parameter space that is most of interest to you with your data set. And if you're worried about using all of your data and then creating more data, you can only use part of your data and do essentially some kind of cross-validation, so using some random partitions of your data. But that's in very short the idea of posterior SPC. For posterior SPC, you need to make a little bit of extra coding around these packages. I think CIMUC is not yet supporting posterior SPC, but I have had talks with Osvaldo Martin, who is actually the developer for CIMUC, so that we could add posterior SPC option for CIMUC also. And in the SPC package, you can run posterior SPC by defining your data your data generating process, so that you create the data not from prior predictive draws but from posterior predictive draws. So a bit of hand coding, but at least you are given quite clear pieces on where to do the changes. And in our paper, I also have a GitHub repository with examples on how to do this.
Yeah, and I put that, so these two packages are in the show notes, both for R and Python. So if I understand correctly, posterior SPC is a bit more computationally intensive than prior SPC. Is that right?
Yes, but only by one model fit.
Yeah.
Because you need to have the posterior, and then you draw posterior predictive samples, and then refit to that. And of course, if you have a very large data set and you have your posterior, and then you create posterior predictive samples, and well, the posterior updating usually happens so that you then just give this essentially double-sized data set and fit that. So if your model fitting is scaling badly by the size of your data set, then it might be computationally more expensive, or then you need to not use your whole observation data set. Yeah, but yes.
Yeah. And so do you recommend always doing both prior and posterior SPC?
Not necessarily. Prior SPC, if it's very hard to reason about your priors, like you have a very complex big model, and setting these priors is not necessarily. For example, you have a very large data set, so your data is anyway going to dominate in your posterior, and your prior is kind of not that impactful. Then you could consider just running posterior SPC. and then essentially focusing on your computational time just to the region that you are actually interested in.
Okay, yeah, I see. That's useful, and like these kind of practical advice. And I'm curious also, what are some of the challenges you faced in developing posterior SBC and even prior SBC, and how did you overcome them? Like when you came up with the methods.
Well, I think one of these challenges is then possibly the inference time. Like you are doing multiple model fits, so sometimes, especially if you are trying to build a model and it's not necessarily the final model, so you're still also in the process of iterating with your models. Stopping to run SBC might not be the optimal workflow. So there you might look at running just very small, short number of simulations just to get like an idea that okay, at least everything is somewhat okay. Like you would detect some gross problems quite quickly. But also what we noticed that like when you're only fitting your model once, it doesn't necessarily impact you so much if the very start of the sampling is slow. But then when you are running 500 or 1,000 refits of your model, yeah. So for example, being smart with how you initialize your MCMC chains might actually come and affect you quite a lot. So in the paper, for one example, I use Pathfinder to get initial states for the chains and then only start MCMC. So it kind of, this requirements for computation kind of gave me challenges that I wouldn't have otherwise considered, but they were actually challenges that you would kind of have anyway if you're fitting your model.
Yeah, no, for sure. I mean, because, I don't think there is that many more challenges anyways because of simulation-based calibration. I mean, the only challenge is you need to feed the model multiple times.
Yeah.
But that's the main bottleneck, right? Because otherwise, like if you have sampling problems, it's not because of SBC, it's because of the model. So yeah, like I can guess that, yeah, if you need some form of variational inference to sample the model, then you'll need that also for SBC, right?
Yeah.
So,
but here we were just in like kind of running a very short Pathfinder chain to come up with initial values for the MCMC. So we were then anyway in the end fitting the model with yeah.
And how, like, what's your experience doing that actually? Because I know that's what Bob Carpenter intended when he developed Pathfinder. So basically to use Pathfinder as an initialization for nuts. In your experience, does that help a lot? And in which circumstances?
In this, like this particular example was a ODE model where especially with the priors, which kind of at first look they look sensible. So when you're setting the priors, you kind of have you have reasons why you put the priors you have there. But what happens is that you quite often generate these multimodal posteriors where there's a very large, like in area, very large posterior mode, and then a very small, very high peak in the density. That's actually the one that you would find more reasonable for like this was a ODE model for a lot of Volterra situation, so predator prey model, and the very large mode was essentially just the posterior mode for where most of the variation in your data was just measurement noise, measurement error. So not necessarily the mode that you would want to explore so much. So Pathfinder was very good at getting the change to start and from the mode that gives you a posterior that actually finds the seasonal trends and dynamics between the species. And also Aki Vehtari has another case study, this birthdays case study, which is in the, if you look at the cover of the Bayesian data analysis book, the 3rd edition, there's a picture from that case study, and there also they have a big GP model where they do also Pathfinder to get good initial values for the chains.